Welcome to Sleep Smart, the place where you come to rest and to wonder at the same time. Here, we believe the best bedtime stories aren't just soothing. They're true. Every episode takes one big idea, something vast, something real, something that's been sitting quietly at the edge of human curiosity, and turns it into a slow, gentle journey told just for you, at just the right pace to carry you toward sleep. Tonight's journey is about something you carry with you every single moment of your life, and yet have probably never stopped to truly wonder about: time itself. We're going to travel all the way back to the very first instant of the universe, before space existed, before a single second had ever passed, and follow time's story forward from there. We'll feel the Earth's first ancient rhythms, long before there were clocks, or calendars, or anyone to watch the sky. We'll walk through ancient civilizations who turned the heavens into calendars of astonishing precision. We'll hear the first mechanical clocks ring out across medieval Europe, and follow ships across oceans guided home by chronometers accurate enough to trust with human lives. We'll sit with Einstein as he discovers that time itself can bend and stretch. And we'll shrink all the way down into the vibration of a single atom, precise enough to hold a second steady for 100 million years. Along the way, we'll slow down and quiet down, together, because that's really what this channel is for. Not just to teach you something new, but to give your mind somewhere gentle to rest while your body lets go of the day. So get comfortable. Settle into your bed. Let your breathing soften. There's nothing you need to do now but listen. Let's begin the story of time. What is time? Close your eyes, if you'd like. You don't need to watch anything tonight. You only need to listen, and let your mind drift, slowly, backward and forward, through the one thing that touches everything that has ever happened. Time. It is the strangest thing we know. We measure it in seconds, in years, in heartbeats. We say we don't have enough of it. We say it's flying by, or dragging on, or standing still. And yet, if someone asked you to hold time in your hand, to point to it, to show it to them the way you'd show them a stone or a leaf, you couldn't do it. We never see time itself. We only see its footprints. A candle growing shorter. A shadow moving across the floor. A face growing older in photographs on a wall. Gray arriving in hair that used to be dark. These are not time. They are only the marks it leaves behind as it passes through the world and through us. So does time really exist, out there, like a river flowing whether we notice it or not? Or is it something we invented? A story we tell ourselves so that the universe feels a little less overwhelming, a little more like something we can organize into mornings and evenings, birthdays and anniversaries, alarms and calendars? Physicists still argue about the answer. Some believe time is woven into the very fabric of the cosmos, as real and physical as space itself. Others believe time is something that emerges, the way wetness emerges from billions of water molecules, even though no single molecule is wet on its own. Perhaps time, too, emerges from something deeper we haven't yet named. We don't need to solve that tonight. Tonight, we only need to follow time's story, from the very first instant it began, 13.8 billion years ago, all the way to this quiet moment, right now, as you lie here, breathing slowly, listening to these words drift past like clouds. Humans have always been fascinated by time, because we are the only creatures, as far as we know, who are aware that it is passing. A tree does not know it is aging. A star does not count the millennia it has burned. But we do. We watch the sun set and feel something. We watch a child grow and feel something. We feel the specific, quiet ache of moments we cannot get back. Maybe that's why, for as long as there have been humans, there have been people looking up, at the sun, at the moon, at the turning stars, trying to catch time in the act. Trying to measure the unmeasurable. That's the journey we're about to take together. We'll start before anything existed at all, before space, before matter, before the first tick of anything we could call a clock. We'll watch time being born alongside the universe itself, in an event so vast it still echoes across everything we can see. We'll walk through the first sunrises and sunsets that ever kept a rhythm, the slow, patient clocks that nature built long before there were eyes to read them. We'll follow our earliest ancestors as they looked up at the same moon you might glance at tonight, learning to read the sky the way we now read the words on a page. We'll walk through ancient temples and pyramids, water clocks and sundials, church bells and mechanical gears, railway platforms and ticking pocket watches, all the way to Einstein, who discovered that time itself bends and stretches depending on how fast you're moving and how strong gravity pulls on you. And at the very end of our journey, we'll rest for a while in the quiet mystery of it all, in the strange, comforting truth that every clock that has ever ticked, every heart that has ever beaten, every star that has ever burned, is part of one continuous story. A story that includes you. Right now. Tonight. So let your body settle into the bed beneath you. Let your breathing slow, on its own, the way it always knows how to do. There is nowhere else you need to be. Nothing else you need to do. Just listen, and let time carry you gently, the way it always has, the way it always will. Let's begin at the very beginning. Before there was a before. When time began. Imagine, if you can, a moment with no before it. Not darkness, because darkness still needs space for light to be absent from. Not silence, because silence still needs space for sound to travel through or not travel through. Try to imagine simply nothing. No space stretching in any direction. No time ticking forward. Nothing to measure and no one to measure it. And then, everything. Physicists call it the Big Bang, though the name is almost misleading. It wasn't an explosion happening somewhere, in some space that already existed, at some moment that was already ticking. It was the beginning of space and the beginning of time, together, at once. There was no outside for it to explode into. Space itself began expanding, everywhere, all at once. And as it did, time began too. Before this instant, the question "what happened before?" may not even mean anything, because before needs time to exist first, and time itself was just being born. Try to rest in that strangeness for a moment. It's all right if it feels almost impossible to picture. Some of the greatest minds in human history have spent their whole lives trying to picture it, and still find it slips away, like trying to hold water in your open hands. In the first unimaginably brief sliver of time, a fraction of a second so small that it would take more zeros to write out than there are stars in the visible sky, the universe was smaller than a single atom, and hotter than anything that exists anywhere today. Space itself stretched outward faster than light, in an event called inflation, ballooning from smaller than a grain of sand to something vast, in less time than it takes a thought to begin forming. As the universe expanded, it began, ever so slightly, to cool. And in that cooling, something remarkable happened. Energy began turning into matter. This is one of the quiet miracles hidden in Einstein's famous equation. Energy equals mass times the speed of light squared. Energy and matter are, in a sense, the same substance, wearing different clothes. As the searing early universe cooled, pure energy condensed into the first particles, quarks, electrons, the tiny building blocks of everything that would ever exist. Minutes after the beginning, not years, not centuries, just minutes, these particles began combining into the simplest atoms, hydrogen and a little helium. This is Quite literally, what stars and galaxies and eventually you and I would one day be made from. The lightest, simplest ingredients in the universe, cooked in the heat of its very first moments. 400 of thousands of years afterward, the universe was a hot, glowing fog, too dense for light to travel far before scattering, the way fog scatters a car's headlights. There was, in a very real sense, nowhere to see, even if there had been eyes to see with. Then, about 380,000 years after the beginning, the universe cooled enough for atoms to fully form, and the fog cleared. Light could finally travel freely. That first light still exists today, stretched out by billions of years of cosmic expansion into faint microwaves that scientists can detect. The oldest light in the universe, a kind of baby picture of everything, still arriving from every direction in the sky. And through all of this, through the expansion, the cooling, the birth of particles and atoms and eventually stars, time was moving forward. Not because a clock was ticking somewhere. There were no clocks yet. Time was moving forward because change was happening, and change is what gives time its direction. This brings us to one of the loveliest, quietest mysteries in physics. Why does time only move one way? Think of an egg breaking, or a puff of smoke drifting apart in the air. You have never seen a broken egg spontaneously reassemble itself, or smoke gather back into a tidy little cloud and disappear into a chimney. Physicists describe this using something called entropy, a measure of disorder. The universe, ever so slowly, tends to move from order toward disorder, from arrangement toward spreading out. And many scientists believe this steady drift toward disorder is what gives time its arrow, why we remember the past but not the future, why eggs break but don't unbreak, why you are older today than you were yesterday, and will be older still tomorrow. At the very beginning, the universe was in an extraordinarily ordered state, all that energy gathered so densely, so uniformly. And ever since, it has been unwinding, slowly spreading out, growing more complex and more scattered all at once. Stars have formed. Stars have died. Galaxies have swirled into being. And every one of these changes is, in its own way, time leaving its fingerprints on the universe. So really, the story of time and the story of the universe are the very same story. They began together, in the same instant. They have been unfolding together ever since, through the birth of galaxies, the birth of stars, the birth of planets, and eventually, on one small blue world orbiting an ordinary yellow star, the birth of something that could look up at the night sky and begin, very slowly, to wonder what time actually was. That's where we're headed next, not into the depths of space, but down onto the surface of a young planet, spinning gently in the dark, where nature was about to build its very first clocks. Let your breathing stay slow and easy. We have a long, gentle night of drifting ahead of us. Nature's first clocks. Long before there was anyone to count the hours, the world was already keeping time. No hands moved across a dial. No bell rang out across a village square. And yet, from the very first days of our young planet, a kind of clock was already ticking, vast, silent, and written into the motion of the earth itself. Picture our planet, newly formed, spinning in the darkness of space. It doesn't spin because anything is pushing it. It spins simply because it was born spinning, out of a swirling cloud of dust and gas that circled our young sun, gathering itself together, faster and faster, the way a figure skater spins faster by pulling her arms in close. That original motion has never really stopped. It has only slowed, ever so slightly, over billions of years. The Earth is still spinning today, carrying you around with it, right now, at roughly 1,000 miles an hour, though of course, you feel none of it, resting here as if perfectly still. Each full turn of the Earth is what we call a day. And built into that single, simple rotation is the very first rhythm life on Earth ever knew. Light, and then darkness. Warmth, and then cool. Waking, and then rest. For nearly all of Earth's history, this was the only clock that mattered. The sun would rise, climb, and fall. The sky would darken, and stars would appear. And every living thing that would ever evolve, every plant, every insect, every fish, every bird, every mammal, would grow up inside this rhythm, shaped by it, tuned to it, long before any of them had a mind capable of understanding what a day even was. Now lift your gaze, gently, to the moon. The moon does not produce its own light, it simply reflects the sun's light back to us, and as it circles the Earth roughly once a month, we see different slivers of its sunlit half, which we call phases. New moon, crescent, half, full, and back again. This cycle, too, became one of nature's early clocks, slower than a day, but faster than a year, offering an entirely different kind of rhythm for early life, and later, for early humans to notice and follow. But the moon does something else, something quieter, something you may have felt without ever quite naming it if you've stood at the edge of an ocean. The moon pulls. Its gravity reaches all the way down to Earth, tugging gently at our planet's oceans, causing the water on the side of Earth facing the moon to bulge slightly outward, and, curiously, causing a similar bulge on the far side of the Earth as well. As our planet spins beneath these two bulges, most coastlines experience rising and falling water twice a day. We call this the tides. And for countless generations of life along the world's coastlines, crabs scuttling with the retreating water, fish following the rising tide into shallow pools, early humans learning exactly when the shellfish beds would be exposed and ready to gather. The tides were their own quiet, dependable clock, moving in patient rhythm with the moon above. Beyond the day and the month, there is a longer, slower rhythm still, the year. As the Earth circles the Sun, a single full orbit taking a little over 365 days, our planet's tilt on its axis means that different regions receive more or less direct sunlight at different points in that orbit. This is what gives us the seasons. Spring's gentle warming. Summer's long, bright days. Autumn's slow retreat into shorter afternoons. Winter's deep, quiet cold. For most of life on Earth, the seasons became perhaps the most important clock of all, because the seasons meant food or the absence of it. They meant warmth or the need to survive without it. Trees learned, over millions of years, to lose their leaves before winter's cold could damage them, and to grow new ones again each spring. Animals learned to migrate, to hibernate, to store food, to breed at just the right moment so their young would be born into warmth and plenty rather than cold and scarcity. None of this required thought, in the way we think of thinking. It required something perhaps even more remarkable: bodies and instincts slowly shaped, generation after generation, by the patient, repeating patterns of the world around them. And then there is a clock closer than any of these, closer, in fact, than anything in the sky. A clock inside you. Nearly every living thing on Earth, from the simplest bacteria to human beings, carries something scientists call a circadian rhythm, an internal cycle roughly 24 hours long, that rises and falls even in the complete absence of sunlight. Deep in your brain, a small cluster of cells acts almost like a tiny, built-in clock, quietly regulating when you feel alert and when you feel sleepy, when your body temperature rises slightly and when it dips, when hormones like melatonin begin to release, gently preparing you for the rest you're settling into right now. This rhythm evolved because, for billions of years, light and darkness were the most reliable, unchanging pattern in the entire world. Any living thing that could anticipate the coming darkness, winding down before night actually fell, or waking in preparation for a sunrise it couldn't yet see, had an advantage over creatures caught by surprise. And so, deep within your cells, echoes of that ancient rhythm still turn, quietly, faithfully, night after night, whether or not you are even aware of it. In a very real sense, you are still keeping one of nature's oldest clocks, right now, as you lie here. Long before pyramids or calendars, before sundials or clock towers, before anyone had counted a single hour, the earth was already turning, the moon was already circling, the tides were already rising and falling, and living things everywhere were already tuned to rhythms far older than memory. This was time before timekeeping. Time as rhythm. Time as breath. Time as the quiet pulse beneath everything alive. And somewhere within this ancient, repeating world, a new kind of creature was slowly emerging, one who would eventually do something no other creature ever had. It would look up at these same rhythms, the sun, the moon, the stars, the seasons, and begin, very slowly, to wonder about them. To notice them. To try to remember them, and predict them, and one day, to write them down. That is where our story turns next. Let your body stay heavy and still. There is nothing to do now but listen, and drift, gently, alongside the same rhythms that have carried life on this earth for billions of years. The first humans discover time. Somewhere, tens of thousands of years ago, a human being lay on the cold ground at night, much as you are lying now, and looked up. Above them, a sky we can barely imagine today, undimmed by any city light, so thick with stars that some ancient peoples described it as a river of light flowing across the darkness. And moving through that river, slowly, night after night, were patterns, patterns that repeated, that returned, that could, if you watched closely enough, be predicted. This was the beginning of humanity's relationship with time, not as something to measure with instruments, but as something to watch, patiently, with nothing but eyes and memory. Our earliest ancestors were hunter-gatherers, moving with the rhythms of the land rather than settling permanently in one place. Their lives depended entirely on knowing when things would happen. When would the herds move to new grazing grounds? When would certain plants bear fruit? When would the rains come, or the frost, or the long stretch of scarcity that came with deep winter? Survival meant becoming, in a sense, a student of time, reading its signs the way we might read a familiar face. The sun was their first and most reliable teacher. It rose in roughly the same place each morning, climbed to its highest point at midday, and set in roughly the same place each evening, though careful watchers would have noticed that these points on the horizon slowly shifted over the course of a year, drifting one direction through the warming months, then reversing and drifting back as the world cooled again. This slow drift was, quietly, the sun tracing out the seasons for anyone patient enough to notice. At night, the stars offered an even richer kind of calendar. Certain constellations would appear on the horizon just before sunrise at certain times of year, and vanish at others, a phenomenon later cultures would name heliacal rising. A particular star climbing into view before dawn might signal, faithfully, year after year, that the rains were coming, or that a migration was about to begin, or that it was time to move camp toward more fertile ground. Long before written language, this knowledge would have been passed down through story and memory, carried in songs, perhaps, or spoken lessons repeated from elder to child around a fire, much like the quiet dark surrounding you now. The moon offered a different, gentler rhythm, one closer to human reach. Its phases, repeating roughly every 29.5 days, gave early humans one of their first countable units of time, longer than a single day but shorter than a full year. Some of the oldest human artifacts ever discovered, small bones marked with sets of notches, dating back tens of thousands of years, are believed by many researchers to be tally marks tracking the phases of the moon. If true, these humble scratches on ancient bone may be among the very first calendars our species ever made. Not carved by kings, not built into monuments, just a person, somewhere in the deep past, quietly keeping count. As generations passed, this careful watching of sun, moon, and stars became bound up with something else profoundly important to human survival: the seasonal movement of animals, and eventually, the growing of food. Many early human groups followed the migrations of the animals they depended on, timing their own movements to match the herds, arriving at calving grounds when the young were born and vulnerable, or gathering at river crossings during predictable seasonal crossings. None of this was guesswork. It was time, carefully observed and remembered, translated into decisions about where to be and when. And then, gradually, in different parts of the world, something changed. Human groups began to settle. They began to plant seeds deliberately, tend them, and wait for harvest, the beginning of agriculture. And agriculture demanded something hunting and gathering never quite had: a need to know, in advance, precisely when to plant. Plant too early, and a late frost could kill the young shoots. Plant too late, and the harvest might not ripen before winter's cold returned. For the first time in human history, timing wasn't just about following what was already happening in the world, it was about predicting, in advance, exactly when to act. This need, more than almost anything else, is what pushed early humans to look even more carefully at the sky, and to begin organizing what they saw into something more formal. Something that could be counted, shared, remembered, and passed down with real precision. The wandering watchers of the stars were, without quite realizing it, laying the groundwork for the very first calendars. And soon, in the fertile river valleys of the ancient world, along the Nile, between the Tigris and Euphrates, along the Yellow River, deep in the jungles of Central America, entire civilizations would rise up, and with them, some of the most extraordinary timekeeping systems the ancient world would ever produce. That's where we're headed next. Ancient civilizations build time. As human beings settled into villages, and villages grew into cities, something remarkable began to happen. The quiet, personal watching of the sky, one person, one set of eyes, one memory, became something shared. Something organized. Something civilizations built together, generation after generation, until watching time turned into measuring it. Let's begin along one particular river, in one of the oldest civilizations to ever formalize a calendar. In ancient Egypt, life depended entirely on the Nile. Each year, with almost perfect reliability, the river would flood its banks, depositing rich, dark soil across the surrounding fields, soil that made Egyptian agriculture extraordinarily productive. And so, quite naturally, the Egyptians built their entire sense of time around this flood. They noticed something else, too. Just before the Nile began its yearly flood, a particular star, the brightest star in the night sky, which we now call Sirius, would reappear on the eastern horizon just before dawn, after months of being hidden below it. This event repeated with remarkable regularity, arriving roughly every 365 days. And so the Egyptians built one of history's first solar calendars around it, a year of 12 months, each 30 days long, with 5 extra days added at the end to keep things aligned. It divided neatly into 3 seasons tied to the Nile's rhythm: the season of flooding, the season of growing, and the season of harvest. The Egyptians also gave us something else we still use every single day, almost without thinking about it: the 24-hour day. Ancient Egyptian astronomers divided the nighttime into 12 hours by watching the rising of 12 particular groupings of stars across the night sky, and, by a kind of natural symmetry, divided daylight into 12 hours as well. 12 and 12. Combine them, and you have the 24 hours still marked on every clock in your home tonight. Meanwhile, in the region between 2 other great rivers, the Tigris and the Euphrates, in what is now Iraq, an entirely different civilization was becoming perhaps the most dedicated skywatchers the ancient world would ever produce. The Babylonians treated astronomy almost like a sacred duty. Generation after generation, their priests and scholars recorded the movements of the sun, moon, and visible planets with astonishing patience and precision, building up centuries of careful observation. It was the Babylonians who gave us the 7-day week, likely built around the 7 moving lights they could identify in the sky: the sun, the moon, and 5 visible planets. And it was the Babylonians, working within a mathematical system based on the number 60 rather than 10, who gave us something you rely on every single time you check a clock: 60 seconds in a minute, 60 minutes in an hour. That single choice, made by scholars in ancient Mesopotamia thousands of years ago, still quietly structures every hour of your life today. Far to the east, ancient India was developing an entirely different, and in some ways far grander, relationship with time. Rather than measuring time only in days, months, and years, ancient Indian cosmology imagined time unfolding across almost unimaginably vast cycles, ages lasting hundreds of thousands of years, nested within even larger ages lasting millions, even billions of years, endlessly repeating in great cosmic cycles of creation and dissolution. Where other civilizations built calendars to organize a single lifetime, or a single agricultural cycle, ancient Indian astronomers and philosophers were, in their own way, contemplating something remarkably close to the deep cosmic time modern physicists would only begin to calculate mathematically thousands of years later. In China, a different kind of precision was emerging. Chinese astronomers developed one of the most sophisticated calendars of the ancient world, a lunisolar system, carefully blending the shorter rhythms of the moon's phases with the longer solar year, and periodically inserting extra months to keep the two aligned. Chinese court astronomers were tasked with observing the heavens with extraordinary care, in part because the calendar was believed to reflect the emperor's harmony with heaven itself. Getting it wrong wasn't simply an inconvenience, it was thought to threaten the stability of the entire empire. Chinese astronomers also kept remarkably detailed records of unusual celestial events, including comets and what they called guest stars, sudden bright new lights in the sky that we now understand were exploding stars, supernovae, some of the very first accurately documented in human history. And on the other side of the world, entirely independently, without any contact with Egypt, Babylon, India, or China, one civilization built what may be the single most extraordinary calendar system the ancient world ever produced. The Maya, living across what is now Mexico and Central America, developed not one calendar, but several, interlocking with one another with breathtaking mathematical precision. a 260-day sacred calendar, a 365-day solar calendar closely tracking the actual seasons, and a long count calendar capable of tracking spans of time stretching across thousands of years, allowing the Maya to record historical dates with a level of long-range accuracy that wouldn't be matched in Europe for centuries. Maya astronomers, working without telescopes, without any of the instruments we take for granted, calculated the length of the solar year and the cycles of Venus with a precision that still impresses astronomers today. Across all of these ancient civilizations, one very human problem remained. How do you measure time during a single day, not just count the days themselves, but track the hours as they pass? The earliest solution was beautifully simple. A stick, placed upright in the ground, casts a shadow that shifts position as the sun moves across the sky. Watch it carefully enough, mark its position at different points in the day, and you have created a sundial, one of humanity's very first timekeeping devices, requiring nothing but a stick, the sun, and patience. But sundials had an obvious limitation. They were useless at night, and next to useless on a cloudy day. So ancient civilizations, independently, in Egypt, in Babylon, in China, and in Greece, developed something cleverer, the water clock, sometimes called by its Greek name, the clepsydra, meaning water thief. Water would drip at a slow and carefully calibrated rate from one container into another, marked with lines indicating the passing hours. As the water level rose or fell, so did the hour. For the first time, human beings could measure the passing of time indoors, at night, regardless of the sun or the weather outside. Other cultures found their own elegant solutions. In parts of the ancient and medieval world, candles were carefully marked with evenly spaced lines, allowing people to track the hours by watching how far the candle had burned down. A gentle, glowing kind of clock, flickering quietly through the night, not so different from the soft light some of you might have burning in your own room right now. In China, some monasteries used a related method, a slow-burning incense stick, sometimes with small weights attached at marked intervals, so that as the incense burned down and the weights fell, they created a small sound, a whispered signal that another hour had passed. What's remarkable, looking back across all of these ancient civilizations, Egypt with its star-guided calendar, Babylon with its 60-based hours and minutes, India with its vast cosmic ages, China with its heaven-watching astronomers, the Maya with their extraordinary interlocking calendars, is that none of them were in contact with one another when many of these ideas first emerged. And yet, again and again, human beings arrived at strikingly similar solutions. Watch the sky, find its patterns, and build something that lets you carry those patterns with you, even when the sky itself is hidden behind clouds, or has set beneath the horizon, or lies deep beneath the darkness of night. Time, once only a rhythm to be witnessed, had become something ancient civilizations could now record, share, predict, and pass down, carved into stone calendars, marked on graduated water jars, whispered in temple astronomy passed from teacher to student across hundreds of generations. But there was still no such thing as a clock in the way we think of one today. No gears, no springs, nothing mechanical ticking forward on its own. That extraordinary leap was still centuries away, waiting quietly in the future, in the cathedrals and monasteries of medieval Europe. That's where our story turns next. For now, rest here a while longer, in this ancient world of shadow sticks and dripping water and slow-burning candles, a world where time was patient and gentle and still deeply, intimately tied to the sky above. From church bells to precision clocks. For thousands of years, Every way humans had measured time depended on something borrowed from nature: the sun's shadow, the slow drip of water, the steady burn of a candle, or a stick of incense. All of these were patient and useful, but all of them depended on something outside human control: sunlight, weather, the careful watching of another person. What the world still lacked was something that could measure time entirely on its own, faithfully, hour after hour, without anyone tending it. That change would begin quietly in the monasteries of medieval Europe. Life in a medieval monastery revolved around prayer, and prayer revolved around time. Monks were expected to gather for worship at specific, fixed points throughout the day and night, a schedule far more demanding than simply rising with the sun and sleeping with the dark. Someone needed to know precisely when to ring the bell calling the community to prayer, even in the deep hours of night, even when there was no sunlight to read and no one awake to watch a water clock drip. This need, precise, reliable, someone doesn't have to watch it timekeeping, is widely believed to be one of the key pressures that pushed European craftsmen, sometime around the late 13th century, toward an entirely new kind of device: the mechanical clock. Unlike a water clock or a sundial, a mechanical clock used weights, gears, and a clever mechanism to regulate motion, allowing a slowly falling weight to turn a set of gears at a steady, controlled pace, rather than simply crashing downward all at once. The earliest of these clocks didn't even have faces or hands the way we picture clocks today. Their entire purpose, at first, was simply to ring a bell at the correct hour, which is where our word clock actually comes from, tracing back to old words for bell. These early machines weren't built to be looked at. They were built to be heard, ringing out across a monastery courtyard, or eventually, a town square, letting an entire community know, without anyone needing to check anything, that another hour had passed. Slowly, these mechanical clocks spread out from monasteries into the towers of churches and town halls across Europe. And as they spread, they began to change something subtle but profound in daily life. For the first time in history, entire communities began organizing themselves not just around sunrise and sunset, but around a shared, external, mechanical sense of the hour. A merchant, a farmer, and a priest, going about entirely different days, could now all hear the very same bell at the very same moment, and know they shared the very same hour. But these early mechanical clocks, for all their ingenuity, were not especially accurate. Left to their own devices, they might gain or lose a considerable amount of time each day, needing to be regularly reset by comparing them, once again, to the ancient reliable clock in the sky, the sun. The next great leap in accuracy came from a rather unexpected place: a teenager sitting in a cathedral watching a chandelier swing. In the late 1500s, a young Galileo Galilei is said to have noticed something curious while watching a lamp gently swaying back and forth in Pisa Cathedral. No matter how wide or narrow its swing became, each full swing seemed to take roughly the same amount of time. Using his own pulse to time it, he began to suspect that a pendulum's swing had a wonderfully consistent, predictable rhythm, regardless of how far it swung. This simple observation, made almost by accident, would eventually transform timekeeping itself. It wasn't until decades later, in the mid-1600s, that a Dutch scientist named Christian Huygens took this idea and built it into an actual clock, using a swinging pendulum to regulate the movement of the gears far more precisely than any weight-driven mechanism before it. The pendulum clock was, almost overnight, dramatically more accurate than anything that had come before it, reducing errors from many minutes a day down to mere seconds. For the first time in human history, A clock could be trusted to keep time almost as faithfully as the sky itself. This new precision arrived at exactly the moment the world needed it most, because human beings were no longer just measuring time on land. They were carrying it out onto the open ocean, where getting it wrong could cost lives. Sailors navigating the vast, featureless expanse of open sea faced an extraordinarily difficult problem. Determining latitude, how far north or south a ship had traveled, was relatively straightforward, simply by measuring the angle of the sun or certain stars above the horizon. But determining longitude, how far east or west a ship had traveled, required something far trickier: an accurate comparison between the local time, determined by watching the sun, and the exact time back at a fixed reference point, like the home port a ship had departed from. The trouble was, no clock of the era could survive the rolling, humid, temperature-shifting conditions of a long ocean voyage while still keeping accurate time. Pendulum clocks, so precise on solid ground, became almost useless swinging on the deck of a ship tossed by ocean waves. For centuries, ships regularly became lost, ran aground, or wrecked entirely, their navigators unable to determine their true position until it was too late. The stakes became so severe that in the early 1700s, the British government offered an enormous cash prize to anyone who could solve what became known simply as the longitude problem. It was eventually solved not by an astronomer, but by a self-taught English carpenter and clockmaker named John Harrison, who spent the better part of his life designing a series of remarkable seagoing clocks, called marine chronometers, capable of keeping extraordinarily accurate time even amid the rocking, humidity, and temperature swings of a long ocean voyage. Harrison's chronometers finally allowed sailors to know, with genuine confidence, exactly where they were on the open ocean, transforming trade, exploration, and naval navigation across the entire world. It's a quiet, remarkable thought, an entire era of global exploration, trade, and discovery, ships crossing oceans, connecting continents, carrying goods and ideas and people across the world, depended, in the end, on humanity's slow, patient mastery of something as simple as an accurate, steadily ticking clock. By the close of this era, time had transformed dramatically from where our story began. What had once been a rhythm read from shadows and stars had become something mechanical, gears turning in monastery towers, pendulums swinging in quiet studies, precision chronometers rocking gently in the hold of ships crossing the Atlantic. Time was no longer simply observed. It was now built, engineered, and carried in a box. And soon, this newly precise, mechanical sense of time was about to collide with something that would change human life more dramatically than almost anything before it: the smoke, steel, and steam of the Industrial Revolution. That's where our journey turns next. For now, let yourself rest in the quiet, steady rhythm of a pendulum swinging gently back and forth, patient and unhurried, the way it has swung for hundreds of years. Time changes civilization. For most of human history, time had been something personal, local, and gently approximate. A village kept its own time, set by its own church bell, calibrated to its own view of the sun. A town a few miles away might be a few minutes off, and it hardly mattered. No one needed to compare their clock to a stranger's clock 100 miles away. Life simply didn't move fast enough or far enough to require it. And then, quite suddenly, in the span of only a few generations, it did. The Industrial Revolution, beginning in Britain in the mid-1700s and spreading across Europe and beyond, brought with it something the world had never quite experienced before: factories. Vast buildings filled with machinery, powered first by water and then increasingly by steam, capable of producing goods faster and in greater quantities than any workshop of individual craftsmen ever could. But a factory only works efficiently if the people working inside it arrive, work, and leave at the same coordinated time. A single spinner working alone at home could begin and end her day whenever she chose. 100 workers operating interconnected machinery in a single factory could not. If even a handful of workers arrived late or left early, the entire production line could stall. And so, for the first time in history, ordinary working people found their daily lives governed not by sunrise, sunset, or the rhythm of the seasons, but by a mechanical clock mounted on the factory wall, and increasingly, by a small device carried in a pocket or worn on a wrist. The factory whistle replaced the church bell as the sound calling people to begin, and later to stop. Workers were now paid, quite literally, by the hour. Time itself had become something that could be bought, sold, and measured out like any other resource. This shift changed something deep in how people related to time itself. Where farmers had once measured a day's work by how much needed doing before darkness fell, factory workers now measured their day by the clock alone, arriving at a fixed hour, working a fixed number of hours, regardless of whether the sun had risen yet or had already set. Time, in a very real sense, had been pulled loose from nature and reattached to the machine. And then came an invention that would make this problem, the problem of everyone needing to agree precisely on what time it actually was, dramatically more urgent: the railway. Before railways, the fact that towns kept slightly different local times, based on their own precise view of the sun, caused almost no trouble at all. A stagecoach traveling between towns took so long that a few minutes difference in local time simply didn't matter. But trains moved fast enough and covered enough distance in a single day that this old patchwork of slightly different local times suddenly became a serious, sometimes dangerous problem. Imagine a train departing a station where the local clock read one time, arriving at a station down the line where the local clock, based on that town's own slightly different reading of the sun, read a different time entirely. Now imagine two trains, on the very same track, each following a schedule based on their own local time, potentially heading toward each other with no reliable, shared way to know exactly when the other was expected to arrive. This wasn't a hypothetical worry, it led to genuine confusion, missed connections, and, tragically, real collisions. The solution that emerged, first across the railway networks of Britain and soon adopted more broadly, was as simple as it was significant: railway time. Rather than each town keeping its own local time based on its own precise solar observations, railway companies began operating on a single, standardized time, usually the time kept in a major city, like London, across their entire network, no matter how far a particular station happened to be from that city. At first, this created an odd, temporary situation where a train station might have two separate clocks, one showing the old local time, and one showing the new railway time, sometimes differing by 10 or 15 minutes. But gradually, town by town, country by country, the practical convenience of a single shared standard won out over the old attachment to strictly local, sun-based time. This idea, of dividing the world into broader zones that all agreed to share a single standardized time, eventually needed to be settled on a truly global scale. In the late 1800s, representatives from around the world gathered at an international conference and agreed on a single reference point from which the entire globe's time zones would be measured, a specific line of longitude passing through the Royal Observatory in Greenwich, England. This became what we now know as Greenwich Mean Time, the 0 point from which every other time zone in the world is still measured today, whether adding or subtracting hours as you move east or west around the globe. In our own era, Greenwich Mean Time has been succeeded by an even more precise standard, known as Coordinated Universal Time, or UTC, a time reference maintained not by watching the sun at all, but by an international network of the most accurate clocks ever built, which we'll come to shortly. But the underlying idea, the one first worked out by anxious railway planners in the 1800s, remains exactly the same. In order for a fast-moving, interconnected world to function safely and smoothly, everyone, everywhere, needs to be able to agree on a single shared version of now. Standing back from all of this, it's worth pausing on just how strange this shift really was. For nearly the entire history of our species, time had been something local, gentle, and tied to the world directly around you. The sun over your own particular horizon, the shadow falling across your own particular field. In barely more than a century, time became something global, synchronized, and abstract. The same precise hour, agreed upon and shared, by people who might never meet, living on opposite sides of the world. And this newly standardized, mechanically precise sense of time was about to be shaken to its very foundations, not by another clever invention, but by a quiet patent clerk in Switzerland, who was about to discover that time itself does not behave the way anyone, in the entire history of human civilization, had ever imagined. That's where our story turns next. For now, let the ticking settle into something soft and distant, a steady, gentle rhythm, carrying you forward the way a train rocks gently along its tracks, into deeper and deeper rest. Einstein breaks time. For over 200 years, one man's idea about time had gone almost entirely unchallenged. Isaac Newton, writing in the late 1600s, described time as something absolute, flowing evenly, steadily, identically everywhere in the universe, completely independent of anything happening within it. In Newton's picture, a clock ticking on Earth and a clock ticking on the far side of the galaxy would, in principle, tick in perfect agreement, marking out the very same universal now, shared by everyone, everywhere, at every moment. It was a comforting, orderly idea. It matched, quite naturally, the way time feels to us in ordinary life, like a single, shared river flowing at exactly the same rate for everyone standing anywhere along its banks. For everyday purposes, Newton's picture worked beautifully. It still works beautifully today, for nearly everything we do, building bridges, launching cannonballs, calculating the orbits of planets, catching a train. But early in the 20th century, a young patent clerk in Switzerland, working quietly on the side of his official duties, began asking a question so simple and so strange that it would eventually unravel Newton's tidy picture of time entirely. His name, of course, was Albert Einstein. And the question that set everything in motion was almost childlike in its simplicity. What would it be like to travel alongside a beam of light? Chasing this question, and combining it with a strange, well-established fact, that light always travels at precisely the same speed, no matter how fast the person measuring it happens to be moving, Einstein arrived, in 1905, at a conclusion so radical that it still unsettles people learning it for the first time. Time is not the same for everyone. Two clocks, perfectly identical, perfectly accurate, can genuinely tick at different rates, depending on how fast each one is moving relative to the other. This isn't an illusion, or a trick of measurement, or something that only appears true because of some limitation in our instruments. It is, according to everything modern physics has confirmed again and again, simply how the universe actually works. Here's one gentle way to picture why. Imagine light bouncing straight up and down between two mirrors, like a tiny ball bouncing between a floor and a ceiling, and imagine using that steady bounce, bounce, bounce as a kind of clock. Now imagine this entire light clock is placed inside a spaceship, moving very fast past you, while you watch from a stationary position. From your perspective, outside the ship, the light doesn't simply travel straight up and down anymore. Because the whole ship is moving sideways at the same time, the light has to travel diagonally to keep bouncing between the same two mirrors, tracing out a longer, zigzagging path. And since light always travels at the very same fixed speed no matter what, a longer path means it necessarily takes more time to complete each bounce. From your outside perspective, that moving clock is ticking slower. Meanwhile, to someone actually riding along inside that spaceship, everything on board feels completely normal. Their own light clock still appears to bounce straight up and down, ticking at its usual, ordinary rate. Each of you, quite genuinely, is correct about what you observe. There is no single, universal, true time that one of you is failing to measure properly. There are simply two different, equally valid experiences of time, depending entirely on how fast each observer happens to be moving. This effect is called time dilation, and it isn't confined to imaginary spaceships. It has been tested and confirmed again and again in the real world. Extraordinarily precise atomic clocks, which we'll return to shortly, have been flown aboard airplanes circling the globe, and when compared afterward to identical clocks that stayed on the ground, the airborne clocks were measurably, if very slightly, out of step. Not because anything was broken. Because time itself, quite genuinely, had passed differently for each of them. And Einstein wasn't finished. A decade later, in 1915, he extended these ideas even further into what's called general relativity, a theory describing not just how motion affects time, but how gravity itself does too. According to Einstein, gravity isn't simply a mysterious invisible force pulling objects toward one another, the way Newton had imagined it. Instead, massive objects, planets, stars, anything with sufficient mass, actually curve the fabric of space and time around themselves, the way a heavy ball placed on a stretched rubber sheet creates a dip that nearby smaller objects naturally roll toward. And remarkably, this curving of space-time doesn't only bend the paths that objects travel through space. It also changes the rate at which time itself passes. The stronger the gravity, the slower time moves. This means a clock sitting at sea level, closer to the enormous mass of the Earth, genuinely ticks very slightly slower than an identical clock placed at the top of a tall mountain, or aboard an orbiting satellite, farther from the planet's gravitational pull. The difference is unimaginably tiny in everyday life, a matter of billionths of a second, but it is real, and it has been measured directly, with extraordinary precision, by physicists using some of the most accurate clocks ever built. If gravity's effect on time seems strange when it's gentle, consider what happens when gravity becomes as extreme as it possibly can be, inside a black hole. A black hole forms when an enormous star, after burning through its nuclear fuel, collapses in on itself under its own crushing weight, compressing an incomprehensible amount of mass into an impossibly small space. The gravity surrounding this collapsed core becomes so overwhelmingly strong that nothing, not matter, not light itself, can escape once it travels close enough. And according to general relativity, time near a black hole slows down dramatically the closer you approach its edge. If you could somehow watch a friend from a safe distance, slowly approaching the boundary of a black hole, a boundary physicists call the event horizon, you would see something profoundly strange. From your perspective, your friend would appear to move slower and slower and slower, their clock ticking more and more sluggishly, their final approach to the boundary seeming to stretch out longer and longer, almost as if frozen, never quite completing. Meanwhile, from your friend's own perspective, nothing unusual would seem to be happening at all. They would simply continue falling forward, their own clock ticking along at its normal, comfortable pace, completely unaware, from the inside, of how strangely their journey appeared to anyone watching from far away. Two true stories about the very same event, unfolding at entirely different rates, depending on where you happen to be standing. It would be easy to imagine all of this as a fascinating but purely theoretical curiosity, elegant mathematics with no real bearing on ordinary life. But remarkably, Einstein's strange, unsettling picture of time quietly shapes something many of us rely on every single day, almost entirely without thinking about it: satellite navigation. The satellites that make modern GPS possible circle the Earth at great speed and at a significant distance from the planet's surface, meaning both of Einstein's discoveries apply to them at once and in opposing directions. Their high speed causes their onboard clocks to tick slightly slower, following the same principle as our imagined light clock aboard a moving spaceship. But their greater distance from Earth's gravity, being farther from our planet's mass, causes their clocks to tick slightly faster, following the principle that weaker gravity means faster passing time. When engineers carefully calculate both effects together, it turns out the weaker gravity wins out, causing GPS satellite clocks to run measurably faster than identical clocks on the ground, by about 38 microseconds each day. 38 microseconds might sound impossibly small, hardly worth noticing. But GPS calculates your location by comparing the precise timing of signals traveling at the speed of light between multiple satellites and your device. Left uncorrected, this small daily drift would cause GPS positioning errors to accumulate at a rate of several miles every single day, quickly rendering the entire system useless for navigation. Engineers designing GPS satellites had to deliberately build Einstein's equations directly into the system, correcting for both effects continuously, just so that the little blue dot showing your location on a map stays accurate. Every time a phone quietly, invisibly pinpoints your location, it is relying on Einstein's strange, beautiful discovery that time is not one single river flowing at the same rate for everyone, everywhere, but something more delicate, more relative, gently shaped by how fast you move and how strongly gravity holds you. Newton's comforting, absolute river of time turned out to be, in truth, something closer to countless smaller streams, each flowing at its own particular pace, depending on where in the universe and how quickly each stream happens to be moving. And with this new understanding of time firmly in hand, physicists and engineers turn toward an entirely new challenge. If time itself could bend and stretch in such subtle ways, how precisely could human beings actually measure it? That question would lead, before long, to some of the most astonishingly accurate machines ever built. Clocks so precise they wouldn't lose a single second in tens of millions of years. That's where our story turns next. For now, let yourself rest in the gentle knowledge that time is moving differently for you right now than it is for someone standing somewhere else entirely, ever so slightly, ever so quietly, and that this strange, beautiful truth changes nothing at all about how peaceful this moment can be. The smallest and most accurate time. By the time Einstein had shown the world that time itself could bend and stretch, humanity's clocks were still, in a sense, old-fashioned things: gears, pendulums, springs, mechanical devices built from metal and motion. If time could be measured with such astonishing subtlety by the universe itself, physicists began to wonder, could human beings build something precise enough to actually detect it? The answer would come not from bigger machines or more elaborate gears, but from something almost impossibly small: the quiet, steady vibration of a single crystal and eventually the inner workings of a single atom. The first great leap in this new direction came in the early 20th century, with the discovery of a curious property in a common mineral called quartz. If you apply a small electrical voltage to a thin sliver of quartz crystal, it vibrates, and remarkably, it vibrates at an extremely precise, extremely consistent frequency, almost like a tiny, silent tuning fork. Engineers realized that if you could count these vibrations accurately and continuously, you could use them to measure time far more precisely than any swinging pendulum or unwinding spring ever could. This became the quartz clock, and it would go on to power something almost every person listening to this now has owned at some point in their life: ordinary wristwatches, wall clocks, and the small timekeeping chips inside almost every electronic device. A typical quartz crystal vibrates roughly 32,000 times every single second, with such remarkable consistency that a simple quartz watch, costing only a few dollars, keeps significantly better time than the finest mechanical pocket watches available to the wealthiest people in the world barely a century ago. But even quartz, for all its improvement, still drifts, very slightly, over time. Enough that a quartz watch might gain or lose a handful of seconds across an entire month. For certain scientific and technological purposes emerging in the 20th century, testing Einstein's theories directly, coordinating global communication networks, eventually guiding satellites through space, even this level of precision wasn't nearly good enough. Scientists needed something almost unimaginably more stable. And they found it, of all places, inside the atom itself. Every atom, it turns out, has its own extraordinarily precise internal rhythm. Electrons within an atom can jump between very specific, very exact energy levels. And each time this happens, the atom absorbs or releases a very particular, unchanging frequency of radiation, a kind of natural, built-in vibration, far steadier and more reliable than anything a human engineer could hope to manufacture from springs or crystals. In the middle of the 20th century, physicists settled on one particular atom for this purpose: cesium. A cesium atom's electrons vibrate between two specific energy states at a frequency so precise and so reliably consistent from one cesium atom to the next, anywhere in the universe, that scientists eventually made an extraordinary decision. Rather than defining the length of a second using anything mechanical at all, they would define it using cesium itself. Today, 1 second is officially defined as the time it takes for a cesium atom to complete exactly 9,192,631,770 vibrations. Not roughly. Not approximately. Exactly. This is what physicists mean by an atomic clock, a device that doesn't count the swings of a pendulum or the vibrations of a crystal, but the extraordinarily precise, naturally occurring oscillations of atoms themselves. And the accuracy involved is almost impossible to hold in your mind comfortably. The finest atomic clocks in use today are accurate to within a single second across roughly 100 million years. If you had started one of these clocks running at the time the dinosaurs still walked the earth, it would, by now, have drifted by less than a single second. An entire network of these atomic clocks, maintained by laboratories and observatories around the world, quietly works together to define something called Coordinated Universal Time, or UTC, the master time standard the entire modern world now runs on. Every time zone on Earth, no matter where you happen to be listening to this right now, is simply defined as some fixed offset, some number of hours ahead or behind this single shared atomic standard. But this precision created an unexpected, quietly poetic complication. Remember that the length of a day is ultimately determined by something far older and far less consistent than any atom: the actual rotation of the Earth, spinning on its axis exactly as it has since our planet's earliest days. And the Earth's rotation, it turns out, isn't perfectly steady. It very gradually slows down, ever so slightly, over time, nudged by the ongoing pull of the moon's gravity and other subtle effects, and it also fluctuates in small, less predictable ways year to year. Clocks, meanwhile, don't slow down or speed up at all. They simply keep ticking, with perfect indifference, at their exact, unwavering rate. This means that, very gradually, the ultra-precise time kept by atomic clocks and the actual, physical rotation of our planet begin to drift apart from one another, ever so slightly. To keep the two in agreement, to make sure that clocks around the world still correspond, on average, to noon, actually meaning the sun near its highest point in the sky, scientists occasionally add what's called a leap second, an extra single second inserted into global timekeeping, allowing the Earth's own ancient, imperfect rhythm to catch back up with the flawless, mechanical precision of the atomic clocks that now govern our modern world. It's a strangely beautiful image, if you sit with it a while. The oldest clock humanity has ever known, the slow, patient spin of the Earth itself, the very same rotation that gave the earliest living things their very first sense of day and night, occasionally needing a gentle nudge to stay in step with the tiny, invisible vibrations of a single atom. This atomic precision doesn't only sit quietly in laboratories. It runs, silently, underneath almost everything in modern life. Every time your phone connects to a cell tower, every time a bank processes a transaction down to the exact millisecond, every time a satellite pinpoints your location on a map, an atomic clock, somewhere, is quietly keeping everything synchronized. The internet itself relies on precise timing to make sure that the countless streams of data flowing between computers around the world arrive in the correct order, correctly assembled, without collapsing into chaos. In many ways, this is a fitting place for our modern understanding of time to have arrived. From a single stick cast into the ground to read the sun's shadow, to the almost unimaginably precise vibration of a single cesium atom, humanity's tools for measuring time have grown more refined, more subtle, and more deeply woven into the invisible rhythm of daily life than any ancient astronomer could possibly have imagined. And yet, for all of this outward precision, atomic clocks, satellites, synchronized networks spanning the globe, there remains something time does inside each of us that no clock, however accurate, has ever been able to fully explain. Why does a single childhood summer seem to stretch on forever, while entire recent years seem to disappear in what feels like a passing afternoon? Why does time itself seem to speed up and slow down, depending on nothing more than what's happening in our own minds? That's where our story turns next, inward, into the quiet, deeply personal experience of time itself. For now, let your own inner rhythm slow, gently, the way it always does at this hour. No atomic precision required, just the old, familiar pull toward rest. Why time feels different. Every clock we've encountered so far, the sundial, the water clock, the pendulum, the atomic clock, measures time the same way, every time, without fail. A second is a second. An hour is an hour. Nothing about the clock itself cares whether you're bored, or delighted, or afraid, or fast asleep. And yet you already know, somewhere in your own experience, that time doesn't actually feel this way at all. A single afternoon spent waiting in a quiet room can feel endless. A single evening spent laughing with someone you love can feel like it lasted only minutes. A car journey towards somewhere new and exciting can feel shorter than the very same drive back home again, retracing the same roads. The clock on the wall insists that all of these moments took exactly as long as it says they did. And yet something inside you insists, just as firmly, that they didn't. This gap, between clock time and felt time, is one of the oldest, gentlest mysteries of human experience. And it turns out, science has quite a lot to say about why it happens. Let's start with one of the most universal observations almost everyone eventually makes. Childhood seems to stretch on forever, while the years after seem to move faster and faster the older we get. Part of the answer lies in something almost mathematical, though it's rarely thought of that way. When you are 5 years old, a single year represents a full 1/5 of your entire life so far, an enormous, sprawling fraction of everything you've ever known. But when you are 50 years old, that same single year represents only 1/50th of your life, a comparatively small, thin sliver against the vast backdrop of everything that came before it. Some researchers believe this simple shift in proportion is part of why each passing year seems to feel smaller and faster the more of them we accumulate. But there's something deeper happening as well, tied closely to memory rather than mathematics. Our sense of how much time has passed isn't actually built from continuously watching a clock. It's built, after the fact, from how much we remember about a given stretch of time, how many distinct memories, how many new experiences, how much novelty our mind had to process and store. Childhood tends to be extraordinarily rich in new experience. Nearly everything is happening for the first time. First days at school, first friendships, first heartbreaks, first summers that feel endless simply because so much new experience is being absorbed and remembered within them. Adulthood, by contrast, often settles into routine. Similar days, similar weeks, similar patterns repeating with only gentle variation. And when the brain looks back over a long stretch of familiar routine, with relatively few standout memories to anchor it, that stretch of time compresses, in memory, into something that feels as though it passed in a blur. This is why a 2-week vacation somewhere entirely new can feel, while you're living through it, like it's rushing by, yet when you look back on it afterward, it can feel like it lasted far longer than 2 ordinary, routine weeks at home. In the moment, novelty makes time feel quick, because your attention is absorbed outward, into new experience, rather than inward, toward counting the minutes. But in memory, that very same novelty makes the stretch of time feel expansive, rich, and long, simply because there was so much of it to remember. Fear and danger reveal another strange wrinkle in how we experience time. Many people who have lived through a sudden accident, a fall, or another moment of genuine danger describe time seeming to slow down dramatically, every detail appearing sharp, vivid, almost frozen, as though the world itself had shifted into slow motion. Researchers who study this effect believe it isn't that time itself actually slows in these moments, but that intense fear causes the brain to lay down memories with extraordinary density and detail, recording far more of the moment than it normally would. When that memory is recalled, so much detail is packed into it that it feels, in retrospect, as though far more time must have passed than actually did. Our sense of time is also deeply tied to attention itself, to where our mind happens to be focused in any given moment. Time spent absorbed in something we find genuinely engaging, whether a fascinating conversation, an enjoyable task, or simply this soothing narration, tends to feel like it passes quickly, precisely because our attention is directed outward, toward the experience itself, rather than inward, toward the passing of time. But time spent bored, waiting, or anxious tends to feel like it drags on endlessly, because in the absence of anything else to hold our attention, we become far more aware of time passing itself, checking clocks, counting minutes, noticing every small increment as it ticks by. And then there is one of the strangest territories of all, where our ordinary sense of time seems to dissolve almost entirely: dreams. Many people have had the experience of a dream that seemed to unfold across what felt like hours, or even days, only to wake up and discover that mere minutes had actually passed. Sleep researchers who study this phenomenon have found that dreaming time doesn't behave anything like waking time. Within a dream, our ordinary internal sense of duration seems to loosen considerably, allowing entire elaborate stories, journeys, and experiences to compress into a comparatively short span of actual physical time. As you drift, over the course of tonight, from wakefulness into sleep, and eventually into your own dreams, you may find yourself slipping into exactly this kind of loosened, elastic sense of time, where minutes might feel like hours, and an entire imagined lifetime might unfold in the quiet space of a single night's rest. Even our biological aging carries its own quiet relationship with time. Every cell in your body is, in its own way, keeping track of time passing, through countless subtle chemical processes, through the gradual wear and repair of tissues, through structures at the tips of your chromosomes called telomeres that shorten very slightly with each cell division, acting almost like a slow, internal biological clock ticking across the years of an entire life. Unlike an atomic clock, ticking with flawless, mechanical precision, or a pendulum swinging in patient, external rhythm, this internal biological clock ticks unevenly, shaped by genetics, environment, stress, rest, and countless other subtle influences, which may be part of why two people who are the very same chronological age can nonetheless seem, in some deep and hard-to-define way, to be experiencing different amounts of lived time within their own bodies. Standing back across everything we've explored so far, it seems that time is, in truth, at least two very different things happening at once. There is the time measured by clocks, steady, mechanical, indifferent, ticking forward at precisely the same rate whether you are joyful or grieving, engaged or bored, awake or dreaming. And there is the time experienced within a mind, elastic, uneven, deeply shaped by memory, attention, emotion, and the simple, quiet accumulation of a life being lived. Both of these are real. Neither one cancels out the other. The atomic clock ticking in a laboratory somewhere is not lying to you when it insists that exactly 1 hour has passed. But neither are you lying to yourself when an hour spent in one kind of moment feels utterly different from an hour spent in another. Perhaps this is one of the quiet, comforting truths tucked inside tonight's entire journey, that clock time and felt time were never meant to perfectly agree with one another. They are simply two different stories, both true at once, both softly at work in this very moment, as the actual minutes on a clock somewhere continue ticking steadily forward, while your own experience of this particular stretch of night settles, gently, into whatever shape your tired mind chooses to give it. And now, as we near the end of our long journey through the story of time, there remain a few final questions, some of the deepest, strangest questions in all of physics, that even our best science still cannot fully answer. That's where we're headed next, into the very edges of what we know. For now, let your own sense of time loosen and soften, exactly the way it always does at this hour, drifting gently from the steady tick of the clock into the quieter, looser rhythm of approaching sleep. The future of time. We've traveled a long way together tonight. From the very first instant of the universe, through the slow turning of the Earth and Moon, through ancient astronomers tracing patterns across the sky, through mechanical gears and pendulums and ocean-crossing chronometers, through Einstein's strange discovery that time bends and stretches, all the way to atoms vibrating billions of times each second inside the world's most precise clocks. And yet, even after all of this, after thousands of years of careful watching, and centuries of increasingly precise measurement, there remain questions about time that even our very best science still cannot fully answer. Let's spend these final quiet moments resting gently among them, not because we need to solve them tonight, but because there's something soothing, rather than unsettling, in realizing that mystery still remains at the very edges of everything we know. One of the questions people ask most often is also one of the oldest. Could we ever actually travel through time? Traveling forward in time, in a very real sense, is something we already know is possible, and something we've already discussed tonight. Einstein's equations tell us that moving fast enough, or experiencing strong enough gravity, genuinely slows your own personal experience of time relative to everyone else's. An astronaut who spent an entire year aboard a space station, orbiting the Earth at tremendous speed, would return home having aged just a tiny, measurable fraction of a second less than everyone who stayed behind. Stretch this effect far enough, travel close enough to the speed of light, or orbit near a black hole's crushing gravity for a while, and in principle, a traveler could return to Earth to find decades, even centuries, had passed for everyone else, while only a comparatively short time had passed for them. This isn't science fiction. It's a genuine, mathematically sound consequence of relativity. We simply don't yet have the technology to achieve speeds or gravitational extremes anywhere close to what would be needed to make the effect dramatic. Traveling backward in time is an entirely different, and far stranger, matter. Some of Einstein's own equations do technically allow for certain exotic theoretical solutions involving what physicists call wormholes, hypothetical shortcuts connecting two distant points in space and time, almost like a tunnel folded through the fabric of the universe itself. In principle, if such a wormhole could exist, and could somehow be held open and stable, it might allow travel not just across vast distances, but across time itself. But here, the vast majority of physicists grow considerably more cautious. Creating or maintaining a stable, traversable wormhole would require forms of matter and energy that, as far as we currently understand physics, may not actually exist anywhere in our universe. Beyond the practical difficulty, backward time travel also raises deeply strange logical puzzles, questions about whether the past could ever truly be altered, or whether the universe would somehow always prevent any change that contradicted what had already happened. For now, backward time travel remains, quite genuinely, in the realm of open, unresolved theoretical possibility, rather than anything close to engineering reality. There's another vast question resting at the far end of time altogether. How, and whether, will time itself ever end? Our universe, as best current physics can tell, is not just expanding, but expanding at an ever-accelerating rate, pushed outward by a still mysterious influence physicists call dark energy. If this acceleration continues indefinitely, as most current evidence suggests it will, our universe faces an extraordinarily slow, quiet fate that scientists have come to call the heat death of the universe. In this scenario, stars will gradually exhaust their nuclear fuel, one by one, over trillions of years, until eventually no new stars are being born anywhere at all. Existing stars will slowly burn out and go dark. Galaxies will drift so far apart from one another, carried by the ever-expanding universe, that eventually even light itself won't have enough time to cross the growing gulf between them. Matter itself, over almost unimaginably vast stretches of time, may slowly decay into its most basic possible components, spreading ever more thinly across an ever-expanding, ever-cooling universe, until finally nothing remains capable of change at all. No burning stars, no forming galaxies, no complexity, no life, no motion of any kind. And here we return to something we touched on right at the beginning of our journey together. Time, in a deep sense, is tied to change. If entropy, that gradual drift toward disorder we discussed back in Chapter 1, ever reaches its absolute maximum, every last bit of usable energy finally spent, every possible change finally exhausted, some physicists believe time itself might, in the most meaningful sense, simply stop mattering. Not because some external switch gets flipped, but because there would be nothing left anywhere in the universe capable of marking one moment as different from the next. It's an almost unimaginably distant fate, still trillions upon trillions of years away, far longer than the universe has even existed so far. There's no need to carry any worry about it into your sleep tonight. If anything, there's something quietly humbling in it. The entire vast story we've walked through this evening, from the Big Bang to atomic clocks to your own heartbeat right now, is itself only a small, early chapter in a story almost incomprehensibly larger still. And this brings us to perhaps the deepest, strangest question of all, the one many physicists now find themselves quietly circling back to: is time truly fundamental, a genuine, basic ingredient of reality, woven into the universe from its very first instant? Or does time somehow emerge from something else entirely, something deeper, something we haven't yet discovered or named? Some of the most advanced areas of modern physics, particularly efforts to unite Einstein's theory of gravity with the strange rules of quantum mechanics governing the smallest particles in existence, have led a number of physicists to a startling possibility: that time, at the deepest possible level of reality, might not be a basic ingredient of the universe at all. Instead, time might emerge, the way temperature emerges from the jostling of countless individual molecules, or the way a wave emerges from the coordinated motion of countless individual water particles, arising from some deeper underlying structure of reality that doesn't, in itself, actually contain anything resembling before and after at all. If this turns out to be true, it would mean that everything we've explored tonight, the ticking of atomic clocks, the swing of a pendulum, the slow turning of the earth, even your own sense of one moment quietly following another as you drift toward sleep, would all be, in some sense, a kind of beautiful illusion resting on top of something even more fundamental. Not a false illusion, exactly the way a mirage might be false, but something more like the way wetness is a real, genuine property of water, even though no single water molecule is wet on its own. Time may be real, genuinely real, and still, at the very same time, emerge from something deeper still waiting to be understood. No one yet knows the answer for certain. It remains one of the true open frontiers of physics, actively being explored by some of the most careful thinkers alive today, and it may not be fully resolved in any of our lifetimes. And perhaps that's exactly the right place for our long journey to arrive, here at its final chapter. Not at a tidy, complete answer, but at the honest, quiet edge of genuine mystery. We began tonight before there was any time at all. We end here, at the very limits of what human understanding has been able to reach so far, still gently unsure whether time is the deepest layer of reality, or simply the surface of something even more profound resting underneath it. Either way, right now, in this particular moment, time is carrying you gently forward, exactly as it has carried every living thing, every civilization, every clock, every star, all the way back to the very first instant of everything. Let's rest there together, for just a little while longer, as our journey draws quietly to its close. Every moment is part of the same story. We've come a very long way together tonight. We began before there was anything at all, before space, before time, before a single before to measure anything against. We watched, together, as that first unimaginable instant unfolded into space, into matter, into light. We watched hydrogen and helium gather into the very first stars, and those stars, over billions of years, forged the heavier elements that would one day become oceans and mountains, and your own quiet, breathing body resting here now. We felt time before there were clocks to measure it, the slow spin of a young earth, the patient pull of the moon on quiet tides, the turning of the seasons that taught the first living things when to grow, when to rest, when to wake. We lay beside our earliest ancestors as they looked up at the same stars, learning, slowly, patiently, to read the sky the way we now read a page. We walked through ancient river valleys, where whole civilizations turned the heavens into calendars, counting days by starlight, tracking years by floods, carving time into stone that has outlasted empires. We heard the first mechanical clocks ring out from monastery towers, watched a pendulum discover its own steady rhythm, and followed ships across oceans, guided home at last by clocks precise enough to trust with human lives. We stood on factory floors and railway platforms as the whole world, almost overnight, agreed to share a single time, a single hour, no matter how far apart people happened to stand. And then we watched all of that careful agreement gently unravel, in the very best way, when a young man wondered what it might be like to ride alongside a beam of light, and discovered that time itself is not one river, but countless quiet streams, each moving at its own true pace. We shrank down, at last, into the vibration of a single atom, precise enough to hold a second steady across 100 million years. And then we turned inward, into the strange, elastic time of memory and dreaming, where a single night can feel like an entire lifetime, and an entire lifetime can feel, looking back, like the length of a single night. Every clock we met along the way, a shadow on the ground, a candle burning low, a swinging pendulum, a cesium atom quietly vibrating in a laboratory, the small ticking rhythm inside your own chest right now, has been marking the very same thing. Not separate times. Just one continuous unfolding, stretching all the way back to that first instant, and reaching, gently, all the way to here. To this breath. To this moment, right now, as your body settles further into stillness, and your thoughts loosen and drift the way they do at this hour. Somewhere above you, whether you can see it tonight or not, the same stars our earliest ancestors once watched are still quietly turning through the sky. Somewhere, an atomic clock is still counting, faithfully, without pause. Somewhere, the tide is still rising, or falling, exactly as it has for longer than there have been eyes to notice it. And somewhere, right here, your own heart is still keeping its own quiet time, one of the oldest, gentlest clocks there is. You don't need to hold on to any of this. You don't need to remember the details, or carry any of it forward into tomorrow. You only need to let it settle, softly, the way everything eventually does, into rest, into stillness, into sleep. The universe will keep its rhythm without you watching tonight.